Okay, so rates of change and introduction to derivatives. This is huge in calculus. And as you're going through here, realizing that your rates of change, you are talking about your change in y over your change in x. And if you've had physics, you know that's going to be translated to delta y over delta x. That's the way you're going to read that. Delta means your change in. So if you've had physics, you're used to seeing the delta. However, if not, then that might be something new to you. Now, you're changing y and changing x's. That means we're going to change our slope formula a little bit. So for our slope formula, we're going to go from that delta y over delta x. That's going to go to f at b minus f at a. So we're going to have f at b minus f at a over b minus a. Remember, slope was your change in y's. This is where in Algebra 1, y'all did y2 minus y1 over x2 minus x1. So that all is talking about an average rate of change. It is your slope formula. It is your changing y's, changing x's. All of that does go together. So in other words, when we draw this, let's say we have a value a here, and let's go up to here. And we're going to make that f at a. And then we're going to go over to b. And I'm just making up places for it. And I'm going to stick f at b right there. And we're going to just have a nice, neat little function going through that. So just going to draw in some kind of little function there. And what I'm going to do is draw a secant line, and keep in mind that secant line is going to intersect our graph in at least 2 points. So y'all see a secant line there, right? Now what's happening here graphically, if I wanted to know the average rate of change from A to B, then I'm going to have f at B minus f at A over b minus a. And that is going to actually be the slope of this secant line. It's the slope of your secant line. That's your average rate of change over a time period. Now, when we talk about average rate of change, a lot of times we call that AROC. And now let's talk about instantaneous speed. That is talking about a specific speed in an instant, at a moment in time. So let's draw that graphically. What would that look like? Well, you've got, again, A, and then you've got some point over here, F at A. And then you've got B, and then somewhere up here, maybe F at B. And we've got some function, again, going through these points. But notice what it tells us. We're looking at instantaneous speed as the slope of a tangent line. So how many times does a tangent line intersect a graph? If it's a tangent line, it's only going to hit it how many times? If we look at example 1, example 1 is just wanting us to write an expression for the average heart rate over a time period. Notice it's from 0 to 90 seconds. You're just talking about an average rate of change. So for this one, you would say that the average rate of change would be equal to, now don't write slope of a secant line here. You don't have a secant line here. It's not talking about lines. It's talking about heart rates. So for this one, it's still that slope formula, but you've got to stay in context of the problem. So it's going to be your heart rate at 90 minus that heart rate at 0 over 90 minus 0. This portion right here, you have to show this step. This is called the quotient, and this is going to be one of the major parts that AP readers are looking for on your free response. It's telling us that we have a roller coaster, and we've got, let's see, after how many seconds do we want? From 2 to 8 seconds, we want the average speed. Okay, so with your average speed, notice that here we're going to look at that time frame. So let's see if we can't set up our quotient. The average rate of change is approximately. I know that the denominator is going to be 8 minus 2, isn't it? That's going to be your duration of your time. So now look at the numerator. That's going to be your distance at 8 minus your distance at 2. Okay, so at D at 8, got 671.36. Okay, minus, and at D at 2, I got 290.54. And all of that is over 6. And so, rounding this out, you've got 63.47. And what would be our units here? What was the distance measured in? Feet, and then the time was seconds. So in part B, we're asked to know what is the average rate or the average speed of the roller coaster from 4 to 6 seconds. So working this out, again, we have our average rate of change is approximately, and we're going to have our quotient, and in the denominator we have 6 minus 4. And so in the numerator we're going to have D at 6 minus the distance at 4. And so from that, whenever you calculate this, you should have 470.18 minus 373.16, and all of that is over 2. And so here our average rate of change should be about 48.51, and the units would be feet per second. All right, so moving on to the other, notice that in part C, we're asked to estimate the instantaneous speed of the roller coaster at exactly 5 seconds. Now, the problem with at exactly 5 seconds is we've only got one value here, and we're looking at our instantaneous speed. So if we're talking about a roller coaster, and it's doing the fall, and you're about right here at 5, then what I want to know is at that instant, what is your speed? So what we need to do is set up our quotient so our instantaneous speed or rate of change is approximately, and keep in mind we know we have exactly 5 seconds. So I know I have a 5 minus, and we need something, over our D at 5 minus something. And so here we need a point that is super duper close to this 5. So in other words, we need to get maybe right about here and say maybe D at 5.01 minus 5.01. And so even if we wanted to approximate even closer, we could also say maybe D at 5 minus D at 5.001. You could even get closer over 5 minus 5.001. So you're getting closer and closer here. Now at 5.01, it looks like you should get a value after your number crunching that value should be 46.714 feet per second. And then over on this one here with the 001, that's going to be about 46.647 feet per second. And so notice here, this is probably close enough for us to take a good estimation. So at exactly 5 seconds, then our IROC, I would say, is approximately 46.67 feet per second. Okay, in example 3, we have traffic flow. And so what we're going to do here, the first part, they want us to calculate our function for t is 8. So we're going to say f at 8 is going to be 92 plus 5 sine of 4. Now you do need to make a note that since you have a trig function, you are in radians. So do make sure the calculator is in radians. And so for this, then we see that f at 8 is going to be about 88.216. So we're going to say that's about 88 cars per minute. Okay, so now let's go through and do some plots here. Notice part B wants us to make a sketch, and so a couple of things that we know about our points here. 92, this sine function, it has been moved up to 92, so it might be a good idea to start here at 80 and then maybe have a point here at 90, maybe 100, and then 110. And then we also know that we have this ordered pair here, 8 and then 88.216. And so here we also have at 0, 92. So at time 0, we're going to start up here, but then we also have a time out here at 8 where it was 88, so it's a little bit below. And so we could continue on way out here and call that at the end of it is 30. So we could call that maybe 28 or something. So with our sine curve, do remember that your sine does circle around. And so we have something like that for our graph. Now look at part C. Part C wants us to estimate our average rate of change, so this is going to be AROC, of the change in traffic flow over the time interval. So here we're going to have our time interval is from 15 to 10, and so we also need our function value. So we're going to say f at 30, or no, f at 15 minus f at 10. And so for that, then we're going to end up with about, because we'll estimate 1.897 cars per minute. Okay, over in part D, they want us to go through and estimate using our intervals. We're going to estimate what the instantaneous rate of change would be at time t equals 8. So we'll go through and set up a couple of different intervals, and notice that the first interval they want us to address is from 8 to 8.1. So looking at that interval from 8 to 8.1, then we're going to have f at 8.1 minus f at 8 all over 8.1 minus 8. And when we type that in our calculators, we're going to get about negative 1.586 vehicles or cars per minute. Okay, and then our next interval we have 8 to 8.01. So we're closing in that distance. So we have f at 8.01 minus f at 8 over 8.01 minus 8. And that's going to give us about negative 1.600 vehicles per minute. And now the last interval they wanted was 8 to 8.001. So then that's going to be f at 8.001 minus f at 8. Again, that is over 8.01 minus 8. And so that's going to be about negative 1.6 vehicles per minute. Okay, so notice that we're going through, and it looks like a negative 1.6 would be a good approximation here. Okay, now look at part E. Why can't instantaneous rate of change of the traffic flow with respect to time be calculated using the method in part D? And so that's going to be because you would end up dividing by 0. So here the statement division by 0 occurs. Okay, for our next example, example 4, then notice we're asked to find the average rate over the 2.5 hours. So that average rate over 2.5 hours, we're going to have f at 150 minus f at 0. And that's going to be all over 150 minus 0. And so that's going to give me 30 minus 1. Or, no, sorry, 30 minus 0 all over 150. And so that's going to be about 1/5. Okay, part B, how fast is the car going between 30 and 50 minutes? So between 30 and 50 minutes, so notice from here to here. So how fast is that car going? Well, it's not going. Notice it's not changing its distance. So here it's going to be 0 miles per minute. Or you can say that the vehicle is stopped. Okay, so when is the car traveling the fastest? So here, looking at it, when would I have the car traveling the fastest? Well, let's look at this slope here. So notice we've got a good steep slope there, and we also have another steep slope here. So I would think that between 0 and 30, and it looks like we've also got the same slope here at 50 up to 80. And notice these are open intervals, so do make sure you keep that open interval there. So what about going the slowest? When is the vehicle going the slowest? Well, that's going to be a super slow slope. So it looks like, so maybe from here to here, that's when we're going the slowest. So we're going to have between 100 and 150. And where is that occurring? That's probably going to be occurring maybe 12 miles per hour, maybe. Okay, so for the next part, we are asked how fast is the car going between t equals 100 and t equals 150. So let's look. We have f at 150 minus f at 100, and that's over 150 minus 100. And so that looks like it's going to be 30 minus 40 over 50. And so that's going to give me negative 10 over 50. And so that's going to give me Let's see, since we're talking about how fast, we do need to take the absolute value or the magnitude here. So we're going to have 1/5, and that's going to be mile per minute. Okay, so look at question F. Why is the segment between 100 and 150 minutes negative? So between 100 and 150, notice that slope, that's going to be, let's see, what do you think might have happened there? Looks like the car probably turned around. Okay. So now let's look at part G. What is the speed of the car at 20 minutes? So at 20 minutes, to find that speed, notice it is on that line segment. So if I knew the slope, that would be wonderful. And so let's see what we're going to have. So we have F at 30 minus F at 0. And that's going to be over 30 minus 0. So that's going to give me 20 over 30. All right, and so now we're going to have, that's going to be 2/3. And we've got mile per minute. And really 2/3 miles per minute, that's not just a normal measurement. So if we really wanted to know, because we're used to saying miles per hour, so if we took 2/3 miles per minute and I multiplied this, because I'm going to multiply 60 to this, because I know in 60 minutes there is really 1 hour. So those minutes will cancel, and that's going to leave me per 1 hour. So here 3 goes into 60, 20. So this looks like it's about 40 miles per hour, if you wanted to know like in normal terms there. So what is the speed of the car at 70? So at 70, we can pick the values around it and set up our slope. So we're going to have F at 80 minus F at 50. And that is all over 80 minus 50. And so that's going to be 40 minus 20 over 30. And so again, that's going to give me 2/3 miles per minute. And if you want to know in real world terms, that's about 40 miles per hour. Okay, so on example 5, you have been waiting in line for 15 minutes to ride the Orlando Eye. It took 10 minutes to ride the ride to the top and 10 minutes to return to the landing level ground, which is near ground level. So what they want us to do here is maybe sketch the time frame and the distance that we've moved there. So starting out, since we've got 10 and 15, I would probably do 5 and then 10, 15, maybe 20, of course 25, and then 30, and then 35, 40, and then of course 45, and then 50. Okay, so starting out, notice you've been waiting in line for 15 minutes. So the distance that you've moved there has been kind of constant for the first 15. So we're going to have just a nice little constant there, waiting in line. And then we get on and notice that it is going to be 10 minutes from here. It's going to be 10 minutes up. So I know right here, we're going to go up 10 minutes, and then we're going to come back down 10 minutes. So when we come back down, that's going to be over here maybe at 35. And then again, you are going to walk again. Let's see, 10 minutes and return to the ground level. So now it's going to go back out this way. You could probably make that a little more rounded. Of course, I can't draw, so there's the idea there of what they were wanting you to do. All right, let's look at the next one. And for this one, it says we've studied projectile motion. So you've got an object, and so projected from the top of a 112-foot building, and its path in seconds is defined by this equation. And we've got a nice table, and it says to use the table to find the average speed between 1.8 and 2.2. So to find that average speed, again, this is going to be our average rate of change. And so our time frame is from 2.2 to 1.8. And so at 2.2, we're at 245.76 minus, and at 1.8, we're 232.96. And so whenever we find that, it looks like we're going to have 32 feet per second. Okay, so now we've got this idea of doing zooming in so tight on a graph that you have something called local linearity. In other words, if you zoom in so close on a point, then everything is going to appear to be a straight line. And so that could be assumed to be a tangent line to the curve at that point. Up here on our graph, the graph to the right represents here, whenever we're doing a really tight interval, then you can zoom in real close and notice that it does look like you're going to be working with a straight line. Okay, and a big part, this summary that we need to look at, really big part on this is the fact that the rate of change in a linear, let me try to get my highlighter here. So the rate of change of a linear function is the slope of the graph. But if we have a curve, then we can approximate the rate of change or the slope at a single point by choosing another point extremely close to that original point. If you find that slope between the 2 points, then you can get a pretty good estimation. So keep in mind here that your approximation will be close to the exact value of the slope that you need or want. That is your instantaneous rate of change or the derivative.